Have you ever pondered upon the fabric of the universe? What if we told you that space and time are not separate, but entwined in a four-dimensional continuum known as SpaceTime? SpaceTime, a concept that might sound like it's straight out of a science fiction novel, is actually a fundamental pillar of our understanding of the universe. It's the mathematical model that fuses the three dimensions of space with the one dimension of time into a single four-dimensional continuum. But hold on a second, this was not always the case. Until the dawn of the 20th century, space and time were considered as separate entities. The universe was believed to be three-dimensional, with time being an entirely separate dimension. But this perception underwent a radical shift with the introduction of the Lorentz transformation and the special theory of relativity, which proposed a different perspective, a unified view of space and time. So, let's unravel the mystery of space-time, a concept that fundamentally changed the way we perceive the universe. Our journey begins at the turn of the 20th century, a time when space and time were considered separate entities. The universe was viewed as a three-dimensional space, where objects existed in terms of locations, shapes, distances, and directions. Time, on the other hand, was seen as a separate dimension, a universal measure of when events occurred within this universe. This was the era of classical mechanics, where time was uniform throughout space and distinct from it. Then came a paradigm shift in our understanding, brought about by the Lorentz transformation and the special theory of relativity. These concepts challenged the established notions of space and time. According to the Lorentz transformation, the state of motion of an observer can affect their perception of space and time. This was a radical departure from the belief that time passed at a constant rate, independent of the observer's state of motion. The special theory of relativity, proposed by Albert Einstein, further expanded on this idea. It suggested that the speed of light is the same for all observers, regardless of their motion or the source of light. This led to the conclusion that time and space could not be absolute entities, but were intertwined in a four-dimensional continuum. This was a revolutionary concept that fundamentally changed our understanding of the universe. The birth of space-time, however, is often attributed to Hermann Minkowski. In 1908, Minkowski presented a geometric interpretation of special relativity that fused time and the three spatial dimensions into a single, four-dimensional continuum. This concept, now known as Minkowski space, was a bold step forward in the realm of physics. It laid the groundwork for the general theory of relativity, where space-time could be curved by mass and energy. It was Hermann Minkowski in 1908 who first presented space-time as a four-dimensional continuum, forever changing our view of the universe. To understand space-time, we must first delve into its basics. Now, before we dive into this journey through the fourth dimension, let's take a moment to consider what we perceive as our reality. We live in a world defined by three dimensions: length, width, and height. These dimensions create the space we inhabit, and we move freely within this space, navigating through it every second of our lives. But here's where it gets intriguing. In the world of physics, there's another player on the field, another dimension that is just as crucial as the three we're familiar with. This fourth dimension is time. Yes, the ticking of the clock, the turning of the pages on your calendar, the transition from day to night and back again. Time is a dimension that we're all immersed in, whether we realize it or not. Now, imagine merging these four dimensions, the three dimensions of space and the one dimension of time, into a single concept. This is space-time, a four-dimensional continuum where space and time are intertwined. Let's introduce a new term here: an event. In the context of space-time, an event isn't a party or a concert, but rather a specific point in space-time. It's defined by a set of four coordinates, 3 for space and 1 for time. For example, imagine a shooting star whizzing across the night sky at a specific moment. That's an event defined by where it happened and when it happened. This concept of space-time is a far cry from our everyday perception of space. In our daily lives, we treat space and time as separate entities. We don't consider the passage of time when we measure the distance between two cities, do we? But in the realm of space-time, space and time are inseparable. They're two sides of the same coin, influencing and shaping each other in ways we're just beginning to understand. In space-time, every event is unique and is defined by its position in both space and time. Now let's explore how space-time plays a crucial role in the theory of special relativity. In the realm of special relativity, a fascinating transformation takes place. Time, as we know it, is no longer an independent, constant entity. Instead, it meshes with the three dimensions of space to form a four-dimensional continuum known as spacetime. Now, imagine an object moving through this spacetime. The rate at which time passes for this object doesn't remain constant. Instead, it depends on the object's velocity relative to the observer. This is a departure from the classical view of time, which was considered a universal, unchanging quantity. To illustrate this, consider a train moving at high speed. To a passenger on the train, time seems to pass normally. But to an observer watching the train from a station, the train's clock appears to be ticking slower. This effect, known as time dilation, is a direct consequence of the way space-time behaves in special relativity. Similarly, there's the concept of length contraction. To the observer at the station, not only does the train's clock seem slow, but the train itself appears shorter than it would at rest. Yet, to the passenger on the train, the length of the train remains unchanged. Both these phenomena, time dilation and length contraction, challenge our classical understanding of time and space. They suggest that time and space are not absolute, but relative. They depend on the motion of the observer. This revolutionary idea was first proposed by Albert Einstein in his special theory of relativity. It was a groundbreaking shift that reshaped our understanding of the universe. It suggested that the fabric of the universe, the spacetime, is not a passive stage where events play out, but rather an active participant that influences these events. So, in the special theory of relativity, space-time is more than just a backdrop. It's a dynamic entity, intricately woven with the events that unfold within it. It's a stage that stretches and shrinks, speeds up and slows down in response to the actors that move upon it. Space-time thus forms the very backbone of Einstein's special theory of relativity. But space-time is not just a static stage where events play out. It's dynamic and can be influenced by mass and energy. Picture a trampoline, flat and taut, suspended in the air. This trampoline is a simple representation of space-time, a four-dimensional continuum that fuses the three dimensions of space and the one dimension of time. Now, imagine placing a heavy bowling ball in the center of the trampoline. The weight of the ball distorts the fabric, creating a dip or a curve. This is the essence of curved space-time, a concept brought to life by the general theory of relativity. In the cosmos, celestial bodies like stars and planets act much like our imagined bowling ball. Their mass and energy warp the fabric of space-time, creating a gravitational field. It's this distortion that creates what we perceive as gravity. So when an object appears to be falling towards Earth, it's actually following the curve of space-time created by Earth's mass. However, it's not just physical bodies that can curve space-time. Energy too plays a role. The more energy an object has, the stronger its gravitational field, and the more it can curve space-time. Think of a star-going supernova. The immense energy released in the explosion significantly warps the surrounding space-time, often resulting in the formation of a black hole. Moreover, this curvature is not confined to the immediate vicinity of a mass or energy source. It extends, influencing the paths of objects even at great distances. This is why planets orbit stars, and why light from distant stars bends as it passes near a massive object. Curved space-time is also responsible for the phenomenon of time dilation, the fact that time runs slower in stronger gravitational fields. This means that a clock near a black hole would tick slower than a clock further away. So not only does space-time define where and when events occur, but it also shapes the very paths those events follow. As we wrap up our journey through space-time, let's take a moment to reflect on what we've learned. We started with the intriguing enigma of space-time, a four-dimensional continuum that beautifully fuses the three dimensions of space and the one dimension of time. We then traced the birth of this concept, which revolutionized our understanding of the universe by challenging the traditional separation of space and time. Delving into the essentials of space-time, we discovered its role in special relativity, where the rate at which time passes depends on an object's velocity relative to the observer. We also explored how space-time curves in the presence of mass and energy, a key pillar of general relativity. This dynamic nature of space-time, its ability to warp and bend, adds another layer of complexity to our universe. Space-time, a concept once unfathomable, is now an integral part of our understanding of the cosmos. As we continue to explore the universe, who knows what new mysteries space-time will reveal.